Hello, my name is Sonika Kurode. I'm in Physics 2211 in Dr. Curtis's class, and this is my drag force lab. So for this lab, I recorded an object falling, and I'll compare the observed model to the predicted computational models to analyze drag. So the first model was observational, where I analyzed the video that I created through Tracker, and Tracker allows us to analyze the real-life scenario of freefall with drag. And then I have two computational models. So the first one is a predicted model, and I created a computational model of free fall without drag and just having gravity using GlowScript. And for the second model for computational model, it was the same, but I included drag in this one. The computational models allow us to see the ideal scenario with exact forces that we enter. And I'm going to compare these two methods to analyze drag. The fundamental physics principles are the force of gravity for freefall, air resistance, which includes drag that slows down falling objects, and Newton's second law, where I used the derived update formulas to see the change in position and velocity over time. And a brief overview of the result is that the computational model, which included drag, was more similar to the observed data. Here's the model. So the system is a tissue and the surroundings are gravity and air resistance, and it had initial conditions of initial position 0, 0, 0, and initial velocity of 0 meters per second. So for the tracker analysis, I dropped the tissue from a height, and the tissue's shape caused drag on the object, which I was able to analyze, and the motion of the free-falling object was recorded here on Tracker. For the code for only gravity, I made the ball's initial position and velocity 0, 0, 0. I made b equal to 0 because this one only talks about gravity, and I kept time to less than 1.6 seconds to match my observed model. I wrote Fnet is equal to ball mass times gravity times j hat, the ball.velocity equal to ball.velocity plus change in time times Fnet over mass, and then ball.position to equal ball.position plus the change in time times the ball's velocity. So for the code that includes drag, I kept the same initial position and velocity, but this time I had a b value of 0.0012. The way I found this was by trial and error until the final point on this model matched my experimental data. And for the net forcing equation, I included drag, so I wrote F drag equals negative b times the magnitude of the ball's velocity squared times the hat of the velocity. I also included weight, which is the gravity force, and then I wrote Fnet is equal to the weight plus F drag. I kept the same ball dot position, the same ball dot velocity. So the graph with drag was higher than the graph with just gravity. This is because drag causes the tissue to fall slower, so it takes a longer time to reach the same final height of negative 1.3 meters. The predicted graph including drag was much more accurate than the just gravity code. As you can see here, the y gravity is much lower, and the y observed and y gravity plus drag are basically about the same points. So some sources of error in this lab could be that the tissue didn't exactly fall straight down, so the x-axis movement could have affected the results, and because I was guessing a b-value, that could have caused some error in the computer model. So for the what does it mean question, the model with drag force can show the terminal velocity. As you can see in the first graph for the velocity versus time on the drag computational model, you can see the velocity becomes constant versus on the only gravity computational model, the velocity doesn't become constant. And for the what if question, if the tissue had an initial velocity, the terminal velocity wouldn't be affected. As you can see here, the first graph doesn't have initial velocity, and the second graph has an initial downwards velocity of 0, negative 5, 0, and you can see that the terminal velocity is reached at about the same time, and the velocity itself is the same. Thank you so much for listening to my lab. I hope you enjoyed.